Так, ну что, я думаю, можно начинать, да? Я начинаю.
Хорошо.
So this is the Topology 2 course, and the present lecture, which is called Applications of Homology, is lecture 8 in the booklet. In the previous lecture, we showed that the three homology theories that we have studied, namely singular homology, simplicial homology, and cellular homology, give the same results. They give the same homology groups and the same induced homomorphisms. In today's lecture, when discussing the applications of homology, I will use whichever homology theory is more convenient in the given context. So let's begin with applications to connectedness. We have the following simple theorem. If X is a topological space and is path connected, then we have H0 of X is equal to Z, and the converse is also true. So how do we prove that? Well, first let's give the proof in this direction. We have our space X, and we must assign to every chain in any zero-dimensional chain in X an integer. Let's do this for an example. Let's consider the chain zero-dimensional chain C equals to, let's say, minus 3A plus 5B, where A and B are points of X, but here they are regarded as zero-dimensional singular simplices. We're using simplicial, we're using singular homology here. Now, to this chain, which is a cycle, because any zero chain is a cycle, I am going to assign the number 2, which is the sum of 5 and minus 3. Now, since the space is path connected, there is a path joining B, and this can be regarded as a singular simplex, a one-dimensional singular simplex. Now, it is obvious from looking at the picture that C is homologous to on the chain C prime, which is equal to 2B. And it's easy to see that this assignment of chains to integers is well defined on homology classes, precisely for this reason. Without going into details, let me say that if we take an arbitrary zero chain, by arguments of the same type as here, we can show that it is homologous to a chain consisting of one zero-dimensional simplex, in that case I was B, and with coefficient equal to the sum of all the coefficients in the given chain. So that's the proof in one direction. The proof in the other direction, is as follows. So we have our space. We know that the zero homology group is Z. So we must prove that given any 2 points, A and B, there exists a path joining these 2 points. How do we do that? Well, we look at A and B as chains with coefficients -1 and +1. Then there is a one-dimensional chain whose boundary is A minus B minus A. So there's some kind of chain, a one-dimensional chain connecting these two chains, or rather a chain whose boundary is precisely the chain B minus A. Now, it is not difficult to prove, and this is a lemma which I leave up to you, that in that case, it is possible to find a path consisting of some of the singular one-dimensional simplexes in a given chain, which joins A and B, and thus proves the theorem. So basically, the proof of this theorem is just to correctly understand what a zero-dimensional homology group is. Now, the next thing that we want to talk about is orientability.
What happens, for example, for spaces that are connected but not path connected, like this weird comb or sign, topology sign?
I don't know, frankly, I don't know if it is a fact that it is probably a fact that if a space is connected but not path connected, then we have.
Oh, so you have as many copies of Z
However,
as
I don't know
path
how,
connected components, right?
pardon me?
You get as many copies of integers as path connected components, right?
Well, if it's path connected, it has one path connected component.
Oh, no, no, yeah, yeah. But when,
I thought you were asking about connectedness because
yeah, yeah, yes, yes.
topological space can be connected without
But
being.
not, yeah, precisely.
Well, I don't know how to prove that we have this equivalent, this if and only if situation for connected spaces. It is, I'm sure it's true, but I don't know how to prove it. So let's go on to orientability.
Okay.
We have the following theorem. Suppose Mn is a connected, smooth manifold of dimension n. Then we have the following equivalence. Mn is orientable if and only if Hn of n is equal to z. Proof. Sorry, I want to add another word here. No. I'm sorry. Not smooth. Triangulated. Compact manifold. So how do I prove that? Well, first, let us recall what an orientable triangulated manifold is. So we have a triangulation. If it is orientable, this means that we can choose an orientation, and each simplex so that the induced orientation on a common n-1 dimensional simplex to two adjacent n-dimensional simplices is opposite. So this orientation this is the orientation of this simplex. It induces this orientation on the common face, and this orientation of this simplex induces the opposite orientation. So if we can orient all the simplices in such a way that we have this condition, then Mn is orientable. Now, let us prove this theorem in the direction from left to right. So we assume that it is orientable, and we want to prove that the homology group is the. Now let us look at the following chain. Denote by the delta Ni the oriented simplices of my manifold. The manifold is compact, so their number is finite. And let us consider the following chain. The sum over I of delta and I multiplied by +1. It is easy to see that this chain is a cycle. Because when we take its boundary operator, notice that now we are in simplicial homology. And the boundary operator in simplicial homology gives us 0 precisely because of this configuration here. So this is a cycle. It is easy to prove that any other cycle is of the form Z multiplied by the cycle that's denoted by C0, the form Z multiplied by C0, where Z is an integer. This is also obvious because if we have a cycle, then it's the boundary operator must be 0, and for that reason, the coefficients of two adjacent simplices have to have the same absolute value, and their signs have to be chosen so that they conform to the orientation of the simplices. Or what you can do, you can initially change the orientation of all the simplices, so that we have this condition, and then our cycle will be written differently with different signs on each of the simplices. And so the condition of the boundary being equal to 0 means that the cycle will have this form with a fixed integer here instead of +1. In the other direction, the proof is quite simple. What we do we choose we take 1, the element 1, or +1 of the integers, and to it corresponds a cycle of the form sum of z I delta and I then we choose the orientation of every simplex. So that this becomes equal to +1 delta and I. And so these new simplices, so tilde here, will give you an orientation of the whole simplex, no, the whole manifold. Okay, so much for orientability. Oh no, there was another theorem about orientability. And this theorem is the following. If Mn is a connected, compact, smooth manifold, then it is orientable if and only if H n of Mn is Z. So before proving the theorem, let me explain what the word orientable means here. What is a smooth orientable manifold? Well, a smooth manifold is a manifold which has an atlas consisting of charts. The transition function from one chart to another are smooth. Now, a chart is a transition function is called positive if a Jacobi matrix is positive, has a positive determinant. And a manifold, smooth manifold is orientable if all the transition functions are positive. It is not difficult to prove that if the smooth manifold is triangulated, then it is orientable in the sense of a smooth manifold, if and only if it is orientable in the sense of a triangulated manifold. This is a rather easy theorem. Now there is a theorem due to Munkres, which says that any smooth compact manifold can be triangulated. And so together, these two facts plus theorem 1 give us a proof of theorem 2. Okay, so much for orientability. And now we go on to more interesting things, some of which will turn out to be rather surprising. Well, the next thing I want to talk about is Betty numbers. And torsion. I will begin with a statement of a theorem which is purely algebraic. And says the following. If G is a finitely generated abelian group, then G is isomorphic to the sum of a certain number of groups isomorphic to the integers plus a finite group. So B is called the Betty number, and T is the torsion group. Now, while you're copying this, let me tell you a little story about Betty numbers. Betty was an outstanding Italian mathematician and physicist, but he did not invent the Betty number. The Betty number was invented by Riemann, but Riemann never published that fact and never published that definition. In fact, Riemann only published 6 papers during his life, a great mathematician who had only 6 publications. And now this terminology, Betty number, arose in the following reason. At the end of his life, Riemann was dying of tuberculosis. And so he moved from Germany to Italy, to a small city of Verbana, where he was ready to meet his death. And in the last years of his life, he did not do any mathematics on his own, and spent his time thinking about the meaning of life, about religion, about philosophical questions, just thinking, not writing anything out. However, clever Italian mathematicians, knowing that he is in Verbana, would visit him and talk to him, and he would gladly talk mathematics with them. And Betty, when he was there, and he visited Riemann many, many times, learned the idea that this number B, which arises in homology theory, as we'll see in a moment, and in a visit to Poincaré, told him about that, and Poincaré was very glad to learn this, and called this number the Betty number, because Betty told him about it. So, end of this little story. And now, this theorem has a corollary. Corollary. If X is a finite simplicial complex, simplicial space, I prefer to say, then it's each of its homology groups X with coefficients in Z, so our usual homology groups, is isomorphic to this.
So this is just because all the homology groups are abelian, right? As we proved before some lectures ago.
Well, homology groups are always abelian.
Yeah, okay.
Uh,
Sure.
X is a finite simplicial space,
Yeah, of
and
course.
the homology group will be finitely generated.
Okay.
And therefore, by this theorem, we have the following.
Yeah, it
proof.
gets all the, yeah. Okay, thank you.
And now we come to a really nice part of this lecture. And this is section 4, and it's called Euler Characteristic. Now you remember that the Euler characteristic was defined for simplicial spaces in a very simple way. It's the alternating sum of the number of simplices of each dimension. So let me write out this definition. So X is a finite simplicial space. Then the Euler characteristic of X is, by definition, the sum k greater than or equal to 0 of -1 to the k by sk or sk is the number of k-dimensional simplices. And we have the following theorem. In the same conditions, so X is still a finite simplicial space. The Euler characteristic is equal to the sum of -1 to the k of the dimensions of X if H k X f now here HK of XF is a homology group with coefficients in the field, or more precisely in the additive group of a field. In that situation, the homology groups are actually linear spaces over that field. So this is a linear space, and dimension means dimension in the sense of linear algebra. And so let us prove this theorem. To do that, we denote by CK, ZK, BK, and HK the chains, cycles, boundaries, and homology groups, homologies, with coefficients in F, where F is a field. So, for example, CK is by definition CK of X F. Okay. Once we have this definition, we can write the following. If we start from 0, go to Z, K, then go to CK, then go to B, K minus 1, we obtain a short exact sequence. There it is. Now let us start computing. Euler characteristic. So Euler characteristic of X is equal to the sum minus 1 to the K of SK, which is the number of simplices of dimension K in X. So this is really equal to the dimension to minus 1 to the K of the dimension of CK. CK is a linear space over F, whose basis consists of all the simplexes of dimension K. So this is just the same thing. And now I am going to rewrite that as follows, as the sum minus 1 to the k of the dimension of zk plus the dimension of bk, or bk minus 1. Now, why do we have that equality here? Well, chains are, because of this exact sequence, chains are either are either cycles or go to boundaries. So this is we obviously have, and the next step is to do a very clever trick. Write the sum minus 1 to the k of the dimension of zk minus the dimension of bk. Now, what have I done? I've raised the index from k minus 1 to k. So in the sum, so what we have here is a sum of the dimension of the big k minus 1 from multiplied by 1 minus k. If I change the summation index, then the sign will change to the opposite sign, and we have this. And now this is obviously the sum of the dimension of hk, because what is the homology group? Hk is just zk by bk. Notice k here. Now, of course, these are not only groups, they're linear spaces. And so we have this simple situation. And from this theorem, we get a remarkable bonus. The bonus is this. Definition. Let X be a topological space, not a simplicial space, a topological space. Then, by definition, the Euler characteristic of X is defined as what? Well, think for a moment, and you will immediately correctly guess that it is the sum of minus 1 to the k of the dimension of h k x with coefficients in the field. So this is a lovely bonus that we get. We get an invariant, an integer valid invariant of topological spaces defined in this way, which is not only a topological invariant, it's also a Markov invariant, as we know. So we now have this very amusing situation in which an arbitrary topological space, which in no way consists of triangles, nevertheless, it has an Euler characteristic. Okay. So the next thing we want to talk about is the Lefschetz fixed point theorem. We'll begin with a definition. Let X be a finite simplicial space let F be a map Oh, sorry, I forgot to turn off my phone. Let F be a continuous map. Not necessarily simplicial, just a continuous map of X to F. Then we consider F K star the induced homomorphism in k-dimensional homology with coefficients in the field of real numbers. This homomorphism is a linear operator. Unlike any linear operator, it has a trace. And we define lambda of f as the alternating sum of traces of our linear operator. So let me remind you of the definition of a trace of a linear operator. Well, if the operator is given in a fixed basis, then it is defined by its matrix. And the trace is simply the sum of all the elements appearing on the diagonal of the matrix. It is a classical fact of linear algebra that the trace does not depend on the basis. And so we have this well-defined number and the main theorem about that is that this is theorem proved by Lefschetz in 1950 something. It says that if the map F of topological space to itself is continuous, then the fact that the Lefschetz number is non-zero implies that F has a fixed point. Which means it has a point x such that f of x equal x. This is the Lefschetz theorem. We're going to prove it now, but before going on to the proof, I have a small remark, and the remark is this, that the Lefschetz number of the identity is precisely the Euler characteristic of x. Because what do you have? What do you have on the main diagonal of the identity map? You have just ones, one, all along the diagonal. So the sum of these ones is the number of simplicities, and the coefficient is the same in the two definitions. So it's just an amusing remark. And now let us go on to the proof of this theorem, which is really very nice. And all you really need is to understand what homology means. To prove the theorem, we'll need a lemma. Hock Lemma, which transfers our considerations from the homology level to the chain level. And the lemma says this: if X is a finite simplicial space, and Fk denotes the chain map of Ck x with coefficients in R to itself. Then we have the following. The sum of -1 to the k trace of k star is equal to the sum -1 to the k of f of the trace of k. Now, let me write these indices in black. To stress the difference between the left and right-hand sides of this equality. This is the induced homomorphism in homology. This is the induced homomorphism on the chain level. So we transfer our considerations to the chain level. So let's go on with the proof of this lemma. As before, we denote by CK, ZK, BK, and HK the chain group, which is a field incidentally, a chain group, not a field, which is a linear space over the field of real numbers. Chain group, cycle group, group of boundaries, group of homologies. Now, let us write out the sequence CK, and I'm going to rewrite it in the following way. It is ZK, all the cycles, plus something else. This is a sum of linear spaces. And now this something else no, sorry. In its turn, dk I will rewrite as bk plus something else. While I'm continuing to do this, you might think a little bit and try to guess what what zk with a hat is. So this whole thing is mapped by the star or dr dk rather to c k minus 1. So we have this picture, and we have the map F. It's induced homomorphism to Fk, and it takes this down to here. And now let's see what happens to these guys. This is mapped by Fk restricted to bk. This is mapped by something which I hope you will guess. So here we get bk downstairs plus z hat k plus c hat k. So this is just and here we have dk. So we have the following picture, and now let's try to figure out, first of all, what is C K hat. Think a little bit. Well, if you understand what homology is, you understand the definition of homology, then this is just bk minus 1. And what is z k hat? Zk hat here. That is the kth homology group, or rather linear space. And this map here is none other than Fk star, this fellow here. And so now let us finish this computation. We have the sum of -1 to the k of the trace of Fk. So this is what we want to compute. We're computing this, and we hope that the result will be the left-hand side here is equal to the sum minus 1 to the k of the trace of this fellow here, fk, restricted to bk, plus the sum, again, minus 1 to the k of f k star. So it's this fellow here that has appeared very nicely on the right-hand side. But it also has, the right-hand side also has some other summands. Minus 1 k of f k minus 1 by b k minus 1. And now we're really done. Because this fellow here cancels with that fellow there. Because what's written here is the same thing, except this is shifted by one of these things. So if you change the summation index from k to k minus 1, and then you get this thing with the opposite sign. So these cancel. And we're left with this, which is what we wanted to prove. So very lovely proof. The only thing you need to do the proof is to understand what homology is in the case when you're working over a field. And in that case, the homology groups are not only groups, they're actually linear spaces. So let me say a few words about we have proved the Hock Lemma, but we have not proved the Lefschetz theorem. So our next step is to prove the Lefschetz theorem by using the Hock Lemma, which, well, I have to erase it, unfortunately, but hopefully you've written it down, and when I'll need it, you'll remember what it is. So this is going to be the proof of the theorem. Proof of the Lefschetz theorem. So we'll prove it by contradiction. So X is a finite simplicial space. So by compactness, so contradiction means that for any X, f of X is not X. By compactness, there exists a number, a positive number, delta, such that the distance between f of X and X is greater than delta. So to speak, the image of a point cannot be infinitely close to the pre-image. Now we do the following. We're going to do two things. First of all, so let me stress that this is true for all X. So we're going to do the following. Remembering that X is a finite simplicial space, we're going to replace F by a homotopic to F, homotopic simplicial map. Phi X to X. But so we're going to do this in an iterated barycentric division of X. So what are we going to do? First, we iterate we take the barycentric subdivision of X many, many times. And after that, we replace the given map F by a simplicial map phi. How many times do we subdivide X? We subdivide it in such a way that the diameter of any simplex is less than delta divided by 15. So these simplices are tiny. And in this subdivision, we replace F by homotopic simplicial map phi. And then, obviously, we have the following. Delta intersected any simplex we take. Delta intersected with the image of delta has to be empty. Well, because you see, each point moves by at least delta. Now, and the simplex where it lives is tiny as compared to delta. So its image is another simplex. And so now we can compute the trace of fk, oh, I'm sorry, of phi k which is, of course, the same as the trace of f, because they're homotopy. The trace of k, and I claim that this is equal to 0 for all k. Why is that? Well, what's in the diagonal? On the diagonal, you have simplices that go to each other, but these move away from each other, so there will be only zeros on the diagonal. R is 0 for this reason. So now we have the sum of traces is 0, and by the Hock lemma, we have the Euler's theorem. So I have just one item I want to talk about, and I have 5 minutes left, and this will be an application of an application, namely the application of the Euler's theorem on 2 vector fields on spheres. So this is vector fields. Fields on spheres. And the main theorem is that if n is even then any vector field, well, smooth, any vector field on a n-dimensional sphere has at least one singular point. The singular point, if you remember, is a point where the vector at that point is equal to 0. And to prove this, we'll do the following very simple construction. We place our n-dimensional sphere into n+1 dimensional space. So here it is. And at any point, we have a vector field. To prove the theorem, we'll prove it by contradiction. We assume that each vector is is non-zero. So this is point x, this is v of x, which is non-zero. Then we do the following. We join the extremity of the vector v of x with the center of the sphere. And it intersects the sphere at some point, which we call f of x. Obviously, the map f is continuous. Now, let us compute the Lefschetz number of f. Well, I claim that it's equal to 1 plus minus 1 to the nth power by the degree of f. Now, the one here is the contribution of the zero-dimensional chain. So this one is the trace of the zero-dimensional in the trace in dimension 0. Dimension 0. Why is that? Well, you think about that, it's easy to understand. Now, this is something which we don't know what it's equal to, except that the degree of f is something, we don't know what it is, but no. The degree of f is 1, sorry, the degree of f is 1. And this number is, because n is even, is +1. So this is equal to +2. and which is non-zero. So it has a fixed point. When does a fixed point occur? A fixed point occurs if and only if the vector v of x at the point x is zero. So this proves. In the case of negative of odd dimension, the question of the existence of vector fields on spheres has a beautiful answer, which I hope you will eventually learn from the exercise class. And so that's all for today. Thank you for your attention.
Thank you.
Okay, so I have to turn this off. And I don't know how to do it. Turn off. If I push on that, what will happen? End meeting for all.